In this session, we'll be moving on to look at vibrating molecules. So moving on from our rotations and our kinetic energy considerations, we'll look at what happens when we consider vibrational quantum numbers. In particular, the effect of finite potential and the effect of tunneling, and where we will find the atoms in a vibrating molecule. So vibrational quanta are the next logical step. We've looked at the quantization of kinetic energy through the particle in the box model, this one on the left, and we've looked at the effect of quantization of angular momentum using those molecular rotations. In each case, we considered only what would happen to the kinetic energy or the angular momentum. We ignored the effects of potential. However, when we start to think of vibrations, we need to combine them to start to consider what happens with potential and kinetic energy. So now we combine the effect of potential and kinetic energy with the harmonic oscillator model. This harmonic oscillator model we talked about in the infrared theory side of the course, but now we're going to look at the quantum mechanics of it. So the harmonic oscillator model formed a parabolic shape. So this parabolic shape, which corresponded to the potential energy curve as a molecule stretches, goes to its equilibrium state, and then compresses again. So the important thing is that we're considering what happens to the energy inside there. At extension and compression, there will be potential energy stored in the spring. At the equilibrium separation, the spring is relaxed, but the atoms themselves are in motion, so there's kinetic energy. And there's this continual conversion between kinetic and potential energy inside this model. So away from equilibrium, atoms are carrying kinetic energy and the bond carries potential, in line with the equation for the harmonic oscillator. The force on the atoms is proportional to the negative k times the extension. This is the very definition of a quantum harmonic oscillator. It's fundamentally different from the 1D box. Inside this well, the potential is not zero, but it is finite. Okay, so it's not an infinite potential, but we do have some there. And it varies as a function of x. Now remember that we can get to the potential by integrating the force. So if we do this, we integrate our force and we end up with the potential being kx squared over 2. So this gives us the fundamental shape of the parabola that we're expecting. Let's now revisit the Schrödinger equation. So the Schrödinger equation has two parts to it. It has its kinetic energy, which carries the symbol T, and the potential energy carrying the symbol V. This is what the Schrödinger equation looks like for a one-dimensional vibration. Remember, with the particle in the box, we ignored the potential because the potential was zero inside the box. But now that we are inside this parabola, this harmonic oscillator environment, we can no longer ignore the potential energy operator. So we integrated it previously, let's now include it in our Schrödinger equation. This is what the Schrödinger equation looks like now for the vibrating diatomic. However, this second-order differential equation, we have to have a wave function which, when operated on by the second derivative and added to itself with a scalar, it returns itself with a scalar quantity. At this point, wave functions become non-trivial. It is not an easy thing to solve this equation, and we're not going to cover it in the context of this course. However, it's useful to be able to see what the outcome is. These wave functions, when we plot them, they look a bit different from the wave functions for the particle in the box. We see the same general trend. We have 0 nodes, 1 node, 2 nodes, 3 nodes, and so on. However, at the edges of the box, things look a bit different. The key points that we want to take away from this: the wave functions don't go to zero at the edge of the well. There is a very small probability of finding the particle outside the bounds. We call this quantum mechanical tunneling, and it's a natural consequence of finite potential. If we have finite potential, we can get tunneling happening, and there is a probability that the particle could be found outside the region we've defined. Another result from this is that we end up with equally spaced energy levels. So remember, with the rotations on a ring and the particle in a box, the energy level scaled with the square of the quantum number, whereas with the vibrating molecule, we have the energy levels spacing equally with quantum number. And finally, the next thing that we have is that a vibrational quantum number of 0 is allowed. So we have a 0-point energy because we have that residual energy from the potential factored in. So no matter what we do, we can never remove all the energy from our vibrating molecule. The wave functions look a bit odd as well because they are asymmetric. It's not so apparent for levels 1 and 2, but if we look at the third one, we see the peaks here are higher than the trough in the middle, and we see the peaks at the edges are higher than the peaks in the middle. So let's have a look at what happens when we consider the probabilities. Remember, if we square the wave function, we get the probability of finding the particle. When we do this for the vibrating diatomic, we get this level of distribution. Again, the key points we wish to see is that the nodes and probability still exist. So as we increase the quantum number, we increase the number of nodes. But we also see that we have a more sizable peak at the edges of the well than we do in the middle of the well. This means the probabilities are greater at the edge. So we are more likely to see a diatomic in its compressed state or its extended state than we are to see it closer to its equilibrium value. At higher potentials, that probability distribution tends to a classical probability distribution. If you think about a vibrating molecule, if you think about picturing what it looks like, it will spend more time extended than it does near its equilibrium state. And that is exactly what we see in the quantum mechanical model. Interestingly, when we think about what's going on at the nodes, well, let's zoom in and think about it a bit more. If we think about the diatomic, we consider the excitation from the ground state v equals 0 to v equals 1. And it's useful to picture what's going on. Remember, the wave function here describes where the nuclei are found. It describes the stretch of the bond. It's not necessarily describing the absolute position in space of each of the atoms. It just describes the length of the bond. At our ground state, the most likely separation is the equilibrium length. This should make sense. If it's not vibrating, we would expect the bond to be around its equilibrium extension. However, when we extend the bond, when we stretch the bond and we allow the molecule to vibrate at v equals 1, we are more likely to see our molecule less than or greater than the equilibrium separation. So our bond will be more likely to be stretched or compressed. But more than that, we have a node at the equilibrium length. There is zero probability that we will find that molecule resting at its equilibrium. There is absolutely no probability of the molecule being at its equilibrium length. So this node is a key observable. Remember, we were talking about nodes in all of our other situations. With the rotations, with the kinetic energy, we still get them for vibrational quantum numbers. And remember that the more energy we have, the greater the vibrational quantum number, the number of nodes increases. So in that respect, it's exactly the same as every other quantum mechanical model we've discussed.